All right, guys, now that we've gone through the theory and the new formula behind how do we solve or how do we create confidence intervals when we have small sample sizes to predict our population mean, let's do a couple examples. Let's go back and figure out our prehistoric horse example. Archaeologists discovered the bones of 7 prehistoric miniature horses and calculates the mean shoulder height of those 7 in the sample to be, let me find it, 46.14 inches. Okay, so in our sample size of 7, the mean shoulder height is 46.14 inches with a standard deviation, X bar, standard deviation of 1.19. We want to find a 99% confidence interval that estimates the mean shoulder height for all prehistoric miniature horses. Well, we know our formula for confidence intervals. We are going to take our point estimate for our population mean, our sample mean. We are going to add and subtract our margin of error. Okay, so we have our sample mean. But we don't know our margin of error yet. So we'll calculate that in a second. 46.14. But what we have to remember is in calculating that margin of error, in order to have an accurate margin of error, we need to be able to discern what's happening in our problem. You see, in our problem, we only have a sample size of 7, and we do not know the population standard deviation. Because of these two things, if we use the critical value based on the standard normal curve and just plug in our sample standard deviation, we are not going to get an accurate margin of error. So what we need to do instead is we'll plug in our sample standard deviation, but our critical value will be based on the t-distribution for sample sizes of 7, which means a degree of freedom of 6. And this will give us our accurate margin of error and consequently giving us an accurate confidence interval. So because we don't know the population standard deviation, and because our sample size is less than 30, we will be taking t of c times s divided by the square root of our sample size. Well, we know our sample size to be, our sample size is 7, and our sample standard deviation is 1.19. Let me double check that, 1.19. So now we need to find our critical value on our t-distribution with a degree of freedom of 6. And we find that by using the calculator function inverse t. So we're going to do 0.5 times 1 plus our confidence level, which is 0.99. Enter in our degrees of freedom. And that gives us a critical value of 3.707, which means to contain 99% of our data on the t-distribution with degree of freedom 6, we need to go 3.707 standard deviations above and below the mean. So we are going to be multiplying 1.19 divided by the square root of 7, our sample standard deviation divided by the square root of the sample size, by our critical value. And that gives us a margin of error of 1.667. And so we plug in that margin of error, and we get a confidence interval for the mean shoulder height of all prehistoric miniature horses. We're trying to predict that. We get a confidence interval of 47.807 down to 44.473 inches. And again, what does that mean? You can write out our explanation here. That means that we are 99% confident that the mean shoulder height for all prehistoric horses is between 44.437 or 473 to 47.807. Another way of thinking about this is based on our specific interval, which was based on our specific sample data. Again, that we could come up with different intervals if we gathered more samples. That because if we gathered a ton of samples, that 99% of those intervals created out of those samples of size 7, 99% of those intervals would contain the true population mean, then we can say that for our specific interval based on our specific sample and sample mean, that we are 99% confident that true mean shoulder height of all prehistoric horses is contained in our interval. It's somewhere contained in our interval. Okay? So in general, now that we've seen an example how to do this, we've got the theory and we've seen an example on how to do this. What we want to solidify up is when do we use what? We have two different formulas for confidence intervals, both very similar in calculation, but slightly different things. And so let's shore up when we use what. So if one of the following is true, this was 9.1, if our sample size is greater than 30, or the population is known to be normal, and we know our population standard deviation, then we can use our confidence interval formula from 9.1. And really what's changing here for our formula is how we calculate the error. If we know the population standard deviation, given that the population is normal, and we have a sample size greater than or equal to 30, then we can find our critical value on the standard normal curve. And we can multiply that by our population standard deviation divided by the square root of the sample size. We also, in this case, are allowed to substitute sigma for S when necessary because that sample size is large. Granted, that is implying that we wouldn't have the population standard deviation. If you do have the population standard deviation, as the second bullet point it illustrates, just plug it in. But if neither of these cases are met, so if we don't know the population standard deviation, which will be most of the time, because usually we don't have accurate population data, and our sample size is less than 30, then we must calculate our margin of error using the critical value those should not be equal to signs. Using the critical value, T of C, from our T distribution, which again, each T distribution is a little different depending on the sample size, multiplied by our sample standard deviation, because again, in this case, the population standard deviation is not known, divided by the square root of the sample size. So be careful in reading your prompt. Your prompt will inform you which error equation you should be using. And again, what you want to really focus on is, do we know the population standard deviation? And do we know the sample size? And when we do know the sample size, is it bigger or less than 30? Thanks for watching. Let me know if you have any questions.